Introduction to Curve Fitting and Linear Regression. This lecture will serve as a basic introduction to curve fitting. We will certainly not cover all methods for curve fitting, but definitely give you a good taste of methods in this category. I think curve fitting is classic computational methods, and it's really neat and fun. It creates really neat graphics and is very useful in scientific and engineering analysis. Before we get into the methods, we have to discuss statistics of data sets. This is things like means, averages, variances to understand that. Once we have that background, then we can jump into our best fit methods. And in this lecture, we'll study linear regression, which has very ugly math. Well, then we'll also study linear least squares, which is essentially implementing the same thing, but in terms of matrices and has much cleaner math. And so when we actually implement this, we'll be implementing linear least squares. First, what is curve fitting? What does that mean? Well, we start off with some kind of sample of data, and these red points here are showing measured values. And for some reason, we know that the physics of what we're measuring, those should fit a Gaussian. But there's noise or error, maybe due to our measurements, maybe due to something else. And we want to fit this as close as possible or figure out what type of Gaussian function fits that the best. So the first thing we'll have to do is come up with an equation for our Gaussian. And so this f of x function is the most generic equation for a Gaussian that I can come up with. And it has an offset, an amplitude, variance or standard deviation, has everything in there. And we have these four variables, A, B, C, and D. A, B, C, and D. And curve fitting is essentially asking the question, what values do A, B, C, and D, what do they need to be so that our function fits those data samples as closely as possible with the minimum amount of error? So in this silly little animation here, we're just trying a bunch of different values of A, B, C, and D. And what you can see is some of them are clearly a better fit, some are a worse fit. One of the things we'll have to do is figure out how do we even quantify how good of a fit something is. And once we have that metric, we can use that metric to then fit our curve. So that's curve fitting. Why do we want to do this? One, we can use it to interpolate. If we have a function at discrete points, maybe we want to know the value between those points. And if we fit to a curve and then use that function to interpolate that point, we can get very accurate values very fast. Maybe we want to find the minimum or maximum of a discrete function. We'll talk more about this when we talk about optimization. Another thing we'll talk about later in this semester is deriving finite difference approximations. If you have a discrete function, how then do you calculate a derivative or second order derivative? Maybe we know the physics of our problem, we know what equation our data should be following, and we will fit our data to that equation, and then from that equation, once we've done the fit, the parameters that come out, like in one of the previous slides, we had A, B, C, and D, we could perhaps ascribe physical meaning to each of those. Also, if we know what the function should be, we can do this just simply to remove noise from the function. Maybe we fit it to a line. This is probably the most common, just to observe trends. You'll see this in stock market analysis. Prices are going up and down. There's lots of noise. But we can fit it to a line or maybe even a parabola and observe general trends. So I'm sure there's even lots of reasons to fit data to curves that I'm not even covering here. There are two basic categories of curve fitting methods. One is a best fit. And this is where you have a bunch of samples and you want to fit your function just as best as possible, understanding that you're going to miss. We'll notice here that these data samples, they don't lie exactly on the line, but we have constructed a line that passes as much through the center of those to represent those as possible. Then there's also exact fits. This comes up when we get to polynomials, where we want those lines to pass through those points exactly. Now let's talk about the statistics of data sets. The first and probably the most common statistic of data sets is the arithmetic mean. And if I was to put this to a geometry perspective, this is as close to the center of all your points as possible. A different type of mean that maybe you have or have not heard of is something called the geometric mean. So rather than adding up all your values dividing by the number of samples, we will multiply all our values and then take the mth root, where m is the number of samples that we have. And this gives you a number that's different than the arithmetic mean, and in some ways it's much more useful. For example, let's say you want to buy a car, and there's certain things you want to know about that car. Does the engine run? Do the brakes work? And so on. And if you were to score all those things, a value of 1 to 10, and let's say the brakes don't work at all, but the engine works wonderfully. If you did an arithmetic mean of a 10 and a 0, you'd have a 5. You'd grade your your car as a 5, and you might buy it. Whereas if the brakes don't work or the engine doesn't run, either one of those, if they're 0, you want the whole metric to be 0 because the car is junk. And the geometric mean takes things like this into account much better. And I tend to use this when it comes to merit functions and optimization. So interesting difference between this and the arithmetic mean. Very often when we have error or noise in our measurements, that noise follows the statistics of a normal distribution or a Gaussian distribution. And we can characterize the width of that one of two ways. And really, it's the same way, just one's the square of the other. So first we have the standard deviation. And this is a parameter that appears in the equation for a Gaussian. And it characterizes the width of the Gaussian, as you can see down here. I'm going back and forth now over the span of plus or minus 1 standard deviation. And what we can see is about 68% of the time, your sample will fall within 1 standard deviation. And then, of course, if we go out to 2 standard deviations, more and more times it falls within that interval. So that's the standard deviation. A very similar parameter, and in my mind is the same thing as standard deviation. In fact, if we just square the standard deviation, we get a parameter called variance. But it is quantifying the same thing as the standard deviation. There's also a parameter used a lot called the coefficient of variation. We won't use that a whole lot in this course, but it is out there. And we can think of this as more of a relative standard deviation. So it's standard deviation, but we're dividing by the mean. So it's normalized in that sense. So we're done with the background, the statistics of data sets. That gives us everything we need to know to then move into curve fitting. And the first one we're going to go through, we won't actually implement. You certainly can implement it, but we won't do that here. And you'll notice that it's pretty ugly math, but I think it's more intuitive math. And it will prepare you for the next curve fitting method. So the goal of regression is when we have a bunch of points with noise to fit it to a curve or a line or some kind of function in a way that minimizes the error or the distance between those samples and the line or any kind of curve. So in this case, we want to fit to a line. And so we have a bunch of measurements here, coordinates x and y, and from these, we want to calculate the equation for a line. And really our goal is to determine this A0 and A1. So how do we do that? The first thing we'll do is write that equation of the line for each of our samples. So for example, we have sample 1, point 1, and so we have the subscript 1 here. So we have our 1 value of y and our 1 value of x, and then of course we have the A0 and A1, which are the parameters of our line. The A0 and A1 don't change for all of these. But then we go to our second point, and we have a 2 subscript on y, 2 subscript on x, but the A0 and A1, they stay the same. So it's the same equation for the line. We're just putting in the x and y coordinates for each of our measured samples separately. And we get a huge list of equations. If we have 20 points, we'll get 20 equations of a line. To write these equations exactly, recognizing that those points have noise in them, we have to add some kind of error term. And that's these E terms over here. We'll call these the residuals. So we know that x1 and y1 is not an exact fit to the line, or at least not necessarily falling right on the line. So by adding some constant here, it lets us write an equals. And really the distance between that point and the line is characterized by that E term. So each equation gets its own E term. If the point just happens to fall on that line, the E term would be 0 for that equation. So those are called our residuals. Well, clearly, we want to minimize those residuals. So we have a problem. We need some kind of quantity that tells us how good our line fits our measured values. So let's think about what a good criteria could be. What if we just added all of the residuals? Would this be good? It turns out that's not good because you will have positive and negative residuals, and they could be relatively large, but if you add them together, we could end up with overall a sum that's near 0, even though we have very large residuals, and it's not a good curve fit. So a sum of residuals is not very good. Recognizing that positive and negatives cancel each other, what if we just took the absolute value of all of the residuals and added them up? Is this a good criteria for best fit? It turns out the answer here is also no, and that's because this does not lead to a unique best fit. We will have multiple solutions of how our line or function can fit those points. Not that this can't be used, it's just that there's something better. So it turns out if we actually sum the squares of the residuals, this leads to a unique fit of our line or function to our measured samples. So we will proceed with this, and we will use that as our criteria for best fit. And after doing this calculation, the capital E is just a single number. Even though we might have hundreds or thousands of individual residuals, we add them all up to get one number telling us how good the curve fit is. So let's look at the equation of the mth sample. So y equals a naught plus x1 times our mth x sample plus the mth residual. We will solve this equation for the residual. So now we have y minus essentially the equation for the line. Notice a few things. What is inside the parentheses is actually the value of y according to our curve fit. The y value over here is our measured value. And that's really why the difference between these two is this residual term or the error. So it's consistent. So now that we have an expression for the mth value of little e, we can substitute this function into our expression for our criteria for best fit. So we replace em squared with this expression, which essentially, remember, is the measured value of y minus our fit value of y, and then plugging in the function above, we get this. Not making much sense yet. Now that we have an equation for calculating E, that single number that tells us how good our fit is, we want to figure out, in this case, what A naught and A1 are that minimizes that. So to minimize something, we'll use the first derivative test or the first derivative rule. And if a function has a minimum or maximum, that means the slope has to be 0 on that minimum or maximum. So we set the first derivative equal to 0 and figure out what value of A naught and A1 makes that happen. Okay, so we have our expression for E. That appears here and here. What we want to do now is differentiate it twice because we have two parameters that we're fitting to. If we had 3 or 4, we'd be taking 3 or 4 derivatives. But we take a partial derivative of our criterion, our error function, with respect to each parameter that we're trying to solve for. So for a naught, we'll take the derivative with respect to a naught, and we bring the derivative to the inside. We calculate the derivative, bring the 2 to the outside, and we end up with an expression. And we do the same thing for a1. We will bring the derivative inside the summation, calculate the derivative, bring a constant to the outside. So we now have these two partial derivatives. They look similar, but they're a little bit different because we differentiated with respect to a different variable. Well, the next step in this first derivative test, we set those derivatives to 0. So we take the expressions that we previously had, set them equal to 0, and do a little bit more algebra in them, and we broke them up. So rather than writing one summation for the a naught partial derivative, we now have 2 summations. And for the a1 partial derivative, we now have 3 summations. So we now have 2 equations and 2 unknowns. This is solvable. These 2 equations, before we solve them, are called the normal equations. When we solve them, we will then be able to calculate a naught and a1 that minimizes that error term e. When we do this, I'm skipping over some algebra here, but here is our answer. We will calculate our a1 based on this big ugly equation that has all those different summations in it. Once we know a1, then it's very easy to calculate a naught, just given the average value of the samples in y and our samples in x. And here's how we calculate our averages. That's pretty easy. And once we have a naught and a1, we've solved our problem. We've done our curve fit. The problem is, yikes, that's a really ugly equation to solve. And it's possible. We can program it into the computer and we can make the computer do all the work. But it turns out there's a much cleaner way to do this using matrices. And that will take us into our next method. Our next method is linear least squares. And it's implementing really what we talked about in the last method, but with cleaner math using matrices. Let's set up our problem and make it a little bit more generic in that we have an arbitrary number of unknowns. So in this equation, the z's we think of as our coordinates. So z0 could be x, z1 could be y, and z2 could be z. But we've generalized this to have any number of terms, but we can think of those as our coordinates. The a0, a1, a2 parameters, those are the unknowns. That's what will fit the curve. And f are our measured values. So that's our problem. We want to calculate the a's given a bunch of measurements. So just like before, we will take this set of equations and we'll add these residual terms. That's what lets us write an equal sign. That's what makes these equations exact, because we know that our measurements won't fall exactly on the curve f. But once we have this large set of equations, one equation for every single one of our measurements, we can cast them into matrix form. We now have a column vector containing all of our values of f. Those are our measurements. We have another column vector containing all our values of a's. Those are our unknowns. That's what will fit our curve to our measurements. We have another column vector containing all of our residual terms. And then we have our matrix essentially containing our coordinates. So rather than keep writing everything like that, we'll write this matrix equation in a more compact form and proceed doing math with those. So now we're in the formulation stage. We need an equation to calculate A. Like before, we took all of our equations and solved for E. We can do this all at once now in matrix form. So we're solving our matrix equation for the E term, our residuals. Step 2, we need our error criterion. And E, we saw that the sum of the squares of the individual residuals was a good criterion. Well, how do we do this when E is a column vector? That's actually pretty easy. We use E as a row vector, multiplying E as a column vector, and if we do the row column thing, we get a single number, which is the sum of the squares. And we can write this a little bit more compactly as E transpose times E. Sometimes that's also called the inner product or the dot product, but it gives us our sum of squares. We have an expression from step 1 for E. It's F minus Z times A. We then calculated our error criterion as E transpose times E. So what we can do is we can take this expression for E and plug it in here to get a new expression for our error criterion in terms of F and Z and A. So remember this error criterion, it's a single number because it was a row vector times a column vector. And before, in our previous method, the way we minimized that was with the first derivative test, and we looked at each of our unknowns one at a time and did partial derivatives. We're going to do the same thing here, but we're going to take derivatives of a matrix equation. Kind of interesting. So here we are with our first original equation, our starting point for the error criterion. We'll take the transpose operation and bring it inside the parentheses. So we just have F transpose, but then the transpose of Z times A, remember we have to swap the order of Z and A, and we get A transpose times Z transpose. And then we still have F minus Z times A on the right-hand side. So we distributed the transpose into the first parenthesis. Then we multiply that out. So we just have essentially the sum and difference of a bunch of terms. Now we're going to observe something. Look at these two terms. Since E is a single number, every single term in this equation has to be just a single number. That means, since these just involve F and Z and A, and both of them are just transposes of each other, they have to be the same because they'll reduce to a single number, and they're transposes of each other. That means we can combine them, and that's really the last step. So we combine the terms and have a slightly simpler equation. On to the next step. Now we're at the point that we have to minimize that error term E. And if you recall in the last method, the way we did that, we took the partial derivative of E with respect to each of our unknown parameters. We are essentially going to do that, the same thing here, except we're going to take the partial derivative with respect to the column vector A. So we're doing it all at once in a single matrix equation. So we start with our original equation for E, and we write our partial derivative, but with respect to the column vector A. So what we'll do now is apply this partial derivative to each term on the right-hand side. So we multiply that out, and we end up here. The first term only has F in it. F is not a function of A, so if we take the derivative with respect to A, that goes to 0. Our second term, the 2 comes to the outside of the derivative operation. And when we take the derivative of our third term, nothing happens right now. Now we do the derivatives. And in this first term, there's only one A. Z and F are not functions of A. We can think of that as coming to the outside of the partial derivative. And then dA is just 1. So really, we're just left with 2 times Z transform F. And we end up here. Over here, we have A twice in this equation. So we can think of that as an A squared. And when we take the derivative of A squared, that 2 comes out. And we only have one occurrence of A now. And of course, we still have the Z transpose Z that we're down here. May seem a little bit weird. With some practice, manipulating matrix equations in this way becomes a little bit more intuitive. So our first derivative test, we have to set that first derivative equal to 0 and then see what our choice was of A that caused that to happen. So notice on the right-hand side, we don't have a bold 0. That's not a column vector of 0. That's just a single number 0 because this E was just a single number. So we set our matrix first derivative, if you will, to 0. We'll not write the derivative operation. We just have our expression equal to 0. Now we need to figure out what A is to satisfy this. So we'll bring this term with the -2 over to the right-hand side. That way we have no negatives, and we can cancel the 2 from both sides. And in some sense, that's our final equation. I'll come back to this in a minute, but let's solve that for A. And we end up here. And in fact, that is our answer to A. And we would call this solving for A in the sense of least squares. Now let's look at this equation, the second to last equation, in a little bit more detail. Right now, just mentally ignore the Z transposes on each side. We have ZA equals F. That really is our original matrix equation, but one that had more equations than had unknowns. So in fact, what we did was just pre-multiply both sides of that original equation by Z transpose. And then we got our answer A. This is a warning slide. If we look at our solution in the sense of least squares, and let's simplify this. So the first thing we'll do is we'll bring our inverse operation in here. So we swap the order, so we just have Z inverse and then the Z inverse of the transpose, and then we just have Z transpose F down here. Now we have the inverse of Z transpose multiplying Z transpose. That gives us the identity matrix, which reduces this whole equation just to Z inverse F. This is the solution to our original equation, but that would have been just the straightforward solution that did not incorporate any sort of least squares. So the moral to the story is we are not free to simplify this because that eliminates our least squares. We actually have to calculate this matrix in here. We'll calculate this column vector and then do the pre-division, solve that by any number of means that we studied earlier in the semester. So don't simplify the least squares equation because it eliminates least squares. A way that I really like to think about this, I'm just picturing the matrices as pictures now, just to kind of get an idea of the size. So if we really have a situation where we have more equations than unknowns, we're going to have rectangular matrix on the left-hand side. And there's many, many, many more equations than there are unknowns. Then we want to multiply this by the transpose of this rectangular matrix on the left. So what happens when we do that? We end up here. The horizontal rectangular matrix is simply the transpose of this vertical rectangular matrix. And we're pre-multiplying both sides of the equation by that transpose. So our next step then is to multiply these two rectangular matrices together, and then also multiply on the right-hand side our horizontal rectangular matrix and our column vector. When we do that, we end up here with a standard AX equals B problem. And our matrix on the left now is square and also a lot smaller. And this is solvable by any number of algorithms, including the ones that we discussed earlier in the course. So in matrix form, here is the least squares algorithm. The first thing we'll do is construct the F and the Z matrix. Remember that Z matrix essentially contains all of the coordinates and the F, the measured values. Once we're there, we just solve for that column vector F, that's the unknowns, following the least squares algorithm. So we will multiply Z transpose times Z. We will then multiply Z transpose times F, and then we will backward divide the two and end up with our A. Once we have A, Now we can extract all of the coefficients that was doing our curve fit, and we're done the problem. So really, anytime we're given a linear algebra equation, ax equals b, and we have more equations and we have unknowns, we can solve this in the sense of least squares. When we do that, it's a best fit, and it's not necessarily exact. So given ax equals b, we will simply calculate a new a and a new b by pre-multiplying by the transpose of a. And now we have a new ax equals b, which has exactly the same number of equations as unknowns, and that's easily solvable. Let's do an example. Here are 4 points, and we would like to fit those to a line. And so the equation of a line that we'll use in this case is y equals mx plus b. Step 1, we write the equation of the line for each one of our points. We have 4 points. And if we put those 4 in matrix form, we end up here. And with practice, you can just do this directly. The step will be obvious. And so from this, we have our measured samples F. That really was this Y column. And then our Z matrix is here. And that's essentially our coordinates. So with practice, we can go straight from our data samples to the F and the Z. F containing our measurements, Z containing the coordinates. To solve this by least squares, we take our vertical Z matrix, if you will, and we pre-multiply both sides of our equation by the transpose. When we multiply these two rectangular matrices together, we get a small square matrix. And on the right-hand side, we multiply our rectangular matrix by our column vector of measurements, and we end up with a small column vector. This is easily solved for the unknown coefficients m and b. The last step in the algorithm, or I should say the second to last step, is to extract m and b. The last step is always to visualize. So that's what we do. We'll plot the original lines. We then calculate our fit curve and plot it through the lines, and we see how good we did. And visually, this looks really good. The line looks like it's essentially passing through the center of our measured data points.